All right, folks, today this is going to get a little more complicated. We're going to start to look at E cell whenever we're not at standard conditions. So whenever the temperature may not be at 298 K, whenever the concentration of our species is not 1 molar and our pressure is not 1 atmosphere. And we're going to introduce this concept of the Nernst equation, and then we'll look at a special type of cell that we call a concentration cell. All right, so what is the effect of concentration on E cell? Well, if we're not at standard state conditions, I've given you this equation previously where we said delta G is equal to delta G standard plus RT ln of Q. Okay, so recall that we said that delta G standard is equal to negative NFE standard, which we could reason then that delta G would be equal to negative NFE. So let's go ahead and substitute in for delta G. So if we have negative NFE is equal to negative NFE standard plus RT ln of Q. If we want to solve for E, we could divide everything by NF. Recall that N is the moles of electrons being transferred and F is Faraday's constant. So after we go through and divide, what we'll end up seeing is that we'd get E, because the negative NF cancels out here and here. That E is equal to E standard minus RT over NF ln of Q. And so sometimes you'll see this written in terms of log, sometimes you'll see this written as the natural log of Q. It just depends. But we have this expression here. This is called the Nernst equation. And typically we simplify it to this if T is equal to 298K, which very often it is. So we can use this equation whenever we're at non-standard conditions. So let's go ahead and try an example really quick. So in here, in this case, what we want to do is we want to find the value of E cell for the following voltaic cell. So we have Fe2 plus is at our anode, we go into Fe3 plus, and then we have silver plus going on to form silver. So what we need to do is we need to do two things. The first thing is we need to find E standard, okay, so E cell. And then after that, we'll have to write a chemical reaction and substitute in for Q. And in this problem, since no information is given about the temperature, we can assume that T is equal to 298K. All right, so let's go ahead and find E cell. So what we'd have to do is we would have to look up the reaction or the reduction potentials for the reaction at the anode and the cathode. So the reduction potential for iron would be Fe3 plus 1 electron yields Fe2 plus, and then we also have to look up Ag plus an electron yields silver. And these standard potentials, okay, so for iron it's 0.771 volts. You'd have to look this up. And here for silver, it's 0.800 volts. Keep in mind that these are reduction potentials, so we're flipping the reaction that's actually occurring at the anode with the Fe2 plus and Fe3 plus. Okay, so we could find E cell by taking E cat minus En. It's not supposed to equal, it's supposed to say minus. Must be a silly goose running around with this red cat and ox. So what we'll find out is E cell is equal to 0.800 volts, because this is with the silver, that's the reaction occurring at the cathode, minus 0.771 volts, which is 0.029 volts. Okay, so right now this looks like a spontaneous process under standard conditions. So now what we need to do is we need to write the balanced chemical equation and think about what Q is going to look like, our reaction quotient. So whenever we write our balanced chemical equation, so we have oxidation occurring, okay, so we have Fe2 plus Ag plus, that's the reduction process, going on to form Fe3 plus plus silver. Okay, so now we're ready to start thinking about using the Nernst equation. So we have E cell is equal to E standard cell minus RT over NF ln of Q. So here, think about what Q would be for this reaction. So recall, for equilibrium constants, or in this case reaction quotients, we don't include solids or liquids in our expressions. We would have the concentration of Fe3 plus over the concentration of Fe2 plus times the concentration of Ag plus. So we'll have to plug this in for Q right here. So we already know E cell standard, so that is 0.029 volts. We're going to assume it's at 298 K. So we can plug in minus 0.0257 volts over, now how many moles of electrons are being transferred? Well, if we look at our half reactions, we can see it's just 1. And the units are already taken care of if we use this constant 0.0257 volts. So just pay attention to that. Then we have the natural log, and then we'll have our reaction quotient. So the concentration of Fe3 plus is 0.20 divided by the concentration of Fe2 plus, which is 0.10, times the concentration of Ag plus, which is 1. So whenever we plug this in, we find that E cell is equal to 0.011 volts. Okay, so we can see that this reaction, the E cell has actually decreased compared to E standard cell, okay, based solely from the concentration of the anode and the cathode species. Let's try another one really quick. All right, so in this reaction, I give you a balanced chemical equation. I give you the concentrations. So the first thing we want to do is find E cell. So we need to write out our half reactions. So we have cobalt 2 plus. Okay, so I'm flipping this around because I need to write the reduction potential out for this. That's not right. It's supposed to be lowercase o. Okay, and then we also have iron, which we have Fe2 plus 2 electrons yields Fe. So in this case, the standard potentials for these, for this first half reactions, it's negative 0.28 volts. And for the second one with iron, it's negative 0.447 volts. These values may differ slightly depending on which table you get them from. And that's okay, because the answer will end up being close enough to whatever answer I have that you will see the point. All right, so we can find E cell. So remember that E cell is equal to E cat minus E an. So we can tell that the iron species is being reduced. So that's the process occurring at our cathode. So we will plug in, and we'll find that E cell is equal to negative 0.167 volts. So this indicates that it's a non-spontaneous process. And now we're ready to go ahead and plug into the Nernst equation to figure out, with the effective concentration and temperature, is this process now spontaneous? So E cell minus RT NF times the natural log of Q. And so now we can plug in for E standard cell is equal to negative 0.167 volts minus 0.0257 volts over how many moles of electrons are being transferred? Well, we can look up here at our half reactions and we see there are 2 moles times the natural log of 0.15, the concentration of our products over the concentration of our reactants. Think about what your reaction quotient is going to look like. And whenever we plug this in, we'll find out that E is equal to negative 0.148 volts. So this reaction is not spontaneous, but we can see that the concentration difference is driving this reaction into a spontaneous direction. And finally, we want to look at concentration cells. So what happens if you have the same anode and the same cathode, and the only thing that's different is you have a different ion concentration. So for instance, in this reaction here, or for this cell, we have zinc at our anode, and then the zinc ions are 0.1 molar. Then at our cathode is still zinc, and zinc 2 plus is 1 molar. So what we've been doing for these concentration differences, the first thing we do is we find E cell. Well, think about it. At both of these, they both have the same half reactions. Okay? Because if you wrote the reduction potentials for both the process at the cathode and the anode, it's this. So that means that E standard cell is equal to 0 volts. So what is the cell potential? Okay, well, we would have E standard minus RT over NF times the natural log of Q. And so now this is the tricky part. You have to think about if you were to write this out into a balanced reaction, what would be in the products and what would be in the reactants. So let's go ahead and use purple to show this. This is the oxidation process because it's at the anode. So we have zinc forming zinc 2 plus with a concentration of 0.10 molar. And then for reduction, we have that zinc 2 plus ion being reduced to form zinc. And this concentration is 1 molar. So if you were to set up Q for this case, your reaction quotient, whenever we get there, we'll have 0 minus 0.0257 volts over how many moles of electrons? Well, 2. The natural log, now we have products over reactants. So we have 0.10 over 1. And we find that E cell is equal to 0.030 volts. So what started out as a reaction at equilibrium, okay, so if we look at the standard cell potential, E cell was equal to 0 right here. But then by using some sort of concentration gradient, we're actually able to make this process spontaneous. So what I urge you to do is to try this next one on your own. And then, let's see, we can see what your final answer should be and you can double check it. Your final answer for this should end up being that E cell equal to 0.021 volts, assuming I plugged everything in correctly. All right, so that does it for the Nernst equation. So go ahead and smash that like button and we'll keep going another day.